Off a bell ringer today. We're going to talk about free fall in a second. Today is kind of the most casual day that you've probably had in here in just a second. The most serious thing that you'll need to do is this problem, but after that, we're going to kind of have just like a very easy conversation. Well, easy maybe not the right word, but it's not as much like take notes, blah blah blah. It's a little more chill. What I'd like you to start off with is this bell ringer. I'm going to give you guys about 2-3 minute head start. My ideal scenario is that you can do this entire problem on your own. One thing I will tell you is this. Oh, I said length of a football field. Let's just go with the actual active part of a football field. In case you didn't know, this football field is 100 yards, and of course the end zones are 10 yards. If you do the whole thing, it's 120. But we're just going to do the 100. Okay. So if I say football field, 100 yards for that. Other thing I'll remind you of before we begin, because it will definitely very much matter here, is if you go to do your given and find, as soon as you have three things, you better be real stupid careful if you feel like you have to fill in a fourth. Because you probably should not be filling in a fourth. Think about that a little bit deeper. All right, 3-4 minutes, and then I'll get going. Do you guys like my shirt? This is my teaching physics on Friday shirt. Sure. Admittedly, it's been a shirt for a lot of different things. It's also my workout shirt. It's a shirt. It's a shirt. It's a good shirt.
Where can I buy the shirt that is shirt?
The internet!
Like, which part of it?
So when I buy the shirt at the shirt store?
The left part?
Like Amazon? Or Prime?
I'm gonna let you figure this one out. And if you can't figure this out, okay, I'm gonna chalk this up to user error.
Oh, man.
In the recording, are you talking?
I shouldn't probably keep talking. Favorite meme right now. Is that a mockingjay?
Yeah, what you do?
It did, yes, 100 yards. 300 feet. By the way, here's a conversion. If you don't know this one off the top of your head, it's usually very helpful. 1 meter is equal to 3.28 feet. It's one that comes up a decent amount of times. So if you have a spot where you're putting a bunch of things, one, I reminded you before, 3.28, yes. 3 conversions that I would regularly either have off the top of my head or written down for easy access. I think I've showed you 1 hour is 3,600 seconds. We start with Dr. rate 1 meter per second is 2.25 miles per hour. And then definitely that last one, that 1 meter is 3.28 feet. Allows you going back and forth between English and metric units a little bit quicker. Now, question ahead of time. Let's play the meta game. Because the question is, does it hit Papa Smurf? Would Spain now remake that problem on just a casual Friday before the weekend. Yeah, let's just nail him. Okay, maybe he does, maybe he doesn't. You have to judge my character on that. I guess I don't know what you're gonna pick. I don't know if I want to know what you would pick in that case. But here we go. Oh no, we got it. Okay. Next page. All right, car's traveling down the road at 60 miles an hour. Here is my basic picture. The picture's probably not going to help us a lot here, but again, we always establish where the zero is and which way is positive. Okay. Here's another thing to probably maybe put in the picture. Here's the displacement, like we talked about yesterday. Now, do I know that Papa Smurf goes at the end of that displacement? No, not inherently. One key thing about this particular problem that you have to understand is it is asking if something happens, not telling you that something is going to happen. So be wary of placing those particular numbers. Now, there's a couple ways to handle this particular problem, but we'll get to that in just a second. Let's put up our 5 variables. Not worrying about any conversions or anything right away. And I would highly suggest that you don't. Just place your numbers down as they go and then work your way after that. What do you know?
Acceleration 60 miles per hour.
What's that?
60 miles per hour.
So what's that? BI. How did I put this up? I should have asked you this thing before, and I didn't. I just kind of went into it. How do I know I used the 5 and not the other, just the 3 like we did the other day? Remember, how do I know whether or not to use the 4 kinematic equations versus that 1 kinematic equation that we talked about? Do you remember the separation there? It's okay. Maybe I'm just asking this wrong. It was whether or not the object is at a constant velocity or not. If it's at a constant velocity, these aren't the 5 that you're going to put down, right? It would be the 3 that go with this equation right here. So the first thing you should always ask in a problem is it at a constant velocity? But of course, maybe you skip past that. Maybe that was too easy. Is it a constant velocity? No, so yes, of course, we need to use the 3. So yep, 60 miles an hour, like you said, is the initial velocity. Okay, what else?
The acceleration is -4.
Nice catch with the negative on that. Absolutely. Okay, why do we see that it's negative?
Because it's slow.
Yeah, it tells us there's an acceleration of 4 meters per second squared, but if we look at the situation well, we see that it's actually negative because the situation is in fact slowing down based on this right here. Okay, next. Final one. Okay, so I'm going to address this. There's 2 ways to handle this. This is definitely the easiest, but I want you to know that technically you could do this problem one of 2 ways. The first way, which we're starting off with, is deciding that the final velocity is 0. And what should probably be my units on this? Yeah, meters per second. So of course it's going to tell me to convert this. Now, here's the next piece that I want to be careful with. So, Papa Smurf is 1 football field away, 300 feet. Okay? Does 300 feet go up here? No. Because of this. Once there are 3 numbers, everything else is set. If these are the numbers, there is an exact amount of space that it takes that car to stop. We don't get to decide what it is, right? Like if I put Papa Smurf 2 feet away from the car, I couldn't go, well, the car's definitely going to stop in 2 feet. No, Papa Smurf's in trouble, right? That's definitely not going to happen. So what are we really doing here? Well, simply put, we're just going to solve for how much displacement is required to stop. And then the question is that above 300 feet? Yes, he got hit. Or is it below 300 feet? Huzzah, we're good. Does that make sense? Questions about that? So again, I'll reiterate that again very quickly. Once you have 3 variables, like we said yesterday, these 2 others are decided. It will take a specific amount of time. It will take a specific amount of distance. So putting in a 4th variable is not going to help because we already know what this is. But that's not what this problem is saying. It's saying, does it make it 300 feet? So that's why we're going to calculate and certainly compare. So first thing I'll do, of course, to make sure my units match is convert that guy. 2.25 miles an hour, 1 meter a second, 27 and change, yes?
I got 26.67 meters.
26.6, yeah, I'll go 26.8, sorry, 26.7, whatever. Right? Am I right, Mama? Cool. Meters per second. The actual kinematics of it all shouldn't be too hard. What equation should we be using? Do you see what I mean about you're probably going to like accidentally memorize these? Yep. VF squared equals VI squared plus 2A delta X. Don't plug in numbers. Oops. Yeah. All right. Don't plug in numbers unless they're zeros. Is there a zero?
Yeah.
Yep. What's zero?
The
Lionel, there we go. Then I'm trying to get delta x, so subtract that on both sides. Divide by 2a. Here we go. Negative 26.7 meters per second squared divided by 2 over negative 4. Oh, what do we got? 2,250 divided by roughly 8. I don't think it hits him, but you guys calculate. So what is it? Better not be negative.
89.9.
That makes more sense. Ooh, it's going to be close. It's going to be close. What do I need to convert that to?
yards.
You could go to yards. I think easier. I don't think anybody needs to convert in here. Like I don't need your conversion in your head between 100 and 300 feet. I think you guys got that pretty easily. So I would just go to feet myself. So 1 meter, 3.28 feet. It's gonna be close. Papa Smurf, one way or the other, is not gonna need to use the restroom after this. That was a little bit gross. I'm sorry. It's Friday.
292.42.
Woo! 292 point what?
292.2.
So does it hit him?
Yes.
He did not. How far is he away?
Oh wait. Oh, 300. Okay. It's
300 feet. Yeah. Okay. So I mentioned at the heart of this problem that there were two ways to potentially do it. This is one. Now, if this was a problem on a test, wink, wink, nudge, nudge, it most definitely is going to be something of this particular effect. It's asking you if something happens. It's not always obvious which one's the easiest way, and a lot of times it comes down to personal preference. What we just did, essentially, mathematically, is this, okay? There were two numbers that were definite. He definitely started at 60 miles an hour, and he definitely was accelerating at -4 in this scenario. But essentially what we did is we plugged in a third variable that asked a question, okay? By plugging in the variable of velocity final is 0, what we're asking the math is if we want to get to a 0 velocity, how far will the car go during that time? Because it definitely will go a particular distance. There is a second thing that you could have done instead of plugging in that 0. Any ideas what it might be, what you could have plugged in ahead of time? It's all right if it's not, I got you. The other thing you could have done is not plugged in the final velocity and plugged in this at 300 feet. Then what would we be asking? How fast is he going after that amount of time? Right? Of course, the answer of that one is a little bit weird because if there is a number, it hits him. Yes? If it's a 0, well, obviously he stops right on time. Okay? If it doesn't hit him, you will get an imaginary number, as you should. Okay? But weirdly, you have to recognize that in that particular circumstance, the imaginary number is correct. Why is it correct? Well, because if it doesn't hit him, what would his speed be at that particular displacement? There wouldn't be a speed. He didn't make it to that particular displacement. Does that make sense? Okay, what you would have ended up with, actually coming back right over here, okay, is, let me just do the conversion for you, because, well, someone do it for me. What's 300 divided by 3.28? 3.28, yeah. 91 point what?
91.56.
So I'm just going to 91.6. So plugging this in, I would have used this equation instead in that case. Cool. That'll work. Okay, I would have done this. This would have been my 26.7 meters per second squared plus 2 times negative 4 meters per second squared times, you said 91.5. Okay, 91.5 meters, 0.5 meters. And the problem is to get VF, you would square root the whole thing. Well, you can kind of see mathematically what happens there. If this distance is too big, then this negative number is going to be bigger than this positive number squared, making there a negative underneath here. And of course, you'll square root the negative and you get an imaginary number. And what I've said about imaginary numbers is that they can't happen in reality. But actually, in this case, that would be your answer. If you get an imaginary number, it could not have done that because it would have stopped earlier. Now, I said at the heart of this, the first way is definitely the easier way to understand. Don't blame you if you're just on that, but there is usually two different ways. And oftentimes the complex way, the reason I'm going to explain it is sometimes the complex way is unavoidable. So you better know how to do that one as well. So anytime we're in this class and I kind of talk about an easy way or a hard way, I'm going to let you kind of judge for yourself what you need. Okay? And I mean that. I don't mean to say that you have to do one thing or the other. If you're like, that easy one he said was the hardest thing for me, then phone in the rest of it, focus on that. This class kind of allows you to choose your own difficulty to a certain degree. If that one was easy for you, cool, focus on the harder one as practice for when it is somewhat unavoidable. Make sense? Cool beans, let's move on. All right, let's talk a number that doesn't yet fully make sense. Freefall. How much did Spainhour say gravity is?
9.8.
Spainhour said gravity was G, or 9.8 meters per second squared. Take a minute or two, okay, hopefully it doesn't take you that long, hopefully we're all on a good page here, and just remind each other, review with everybody in your group what the heck that number actually means is going on with objects up in the air. This is the number, this is what we've told you it is. What does that mean objects in the air are doing with that number? Discuss quickly for a minute, so we'll be right back after these messages. All right, so who feels like they got it? Let's go.
Sorry.
Go ahead.
The velocity changes when something is falling by 9.8 meters per second.
Every second. Correct. Yes. If you struggle with it, here's the definition. Okay? As we get later in this chapter, a lot of times we get further away from the conversation on acceleration, especially if it's not like you really understand it. A lot of times people will start to think of it like this. Hopefully you're already like, no, these are not the same at all. This is how fast it's going. This is how much it changes every single second. Okay? Again, when we do quick calculations, I usually roughly assume 10 for the sake of this particular thing. With that, I should be able to say, hey, Spainhour throws an object in the air at 30 meters a second. How long should it take to get to the top? About 3 seconds. Why? Because after 1 second, how fast is it going? 20. After 2 seconds, it's going 10. After 3 seconds, it's going 0. Why? Because it changed by 10 every second. Does that make sense-ish? Cool. Now, that all being said, knowing that number is great, anybody have any issues with that number whatsoever? According to Spainhour, that is the acceleration in the air of everything. Everybody cool with that? Or we want to actually address the fact that Spainhour might be a liar and there's something weird in our hearts here? What do you got? What's your issue?
It's only the gravity on Earth.
Sure, certainly. Okay, my apologies. I did not mean, let me rephrase the sentence because that is completely fair. This is the acceleration of gravity on Earth. Now you good, or you still have issues?
About friction.
Okay, all right, so on further. Okay, we'll go with it. No, we won't go with friction. We won't take that one out. Yeah, friction's part of it, certainly. I wouldn't say that should be your biggest constraint yet, your biggest struggle.
It might be less.
Could be lying, but let's forget the Spainhour effect slide. Let's actually figure out. What you got there? Yeah. According to Spainhour, this accelerates at the exact same amount as, let's not do that. as a feather or a piece of paper. So let's put your understanding to the test. Let's see if you believe him or whether or not we think he's actually a liar. So here we go. Sorry, people online, you're just going to have to, I'll try to describe what's happening. I'm about to drop a piece of book in a paper. I know a piece of book, it's just 100% a piece of book. All right, okay, so I'm going to drop a book and a piece of paper. Okay, I want you guys to vote on this, and when we vote in here, we're going to be very un-American. I expect 100% of people to put up an answer, even if you don't know, because that's freaking science. There's some bad scientists out there, they still get a vote. All right, here we go. They're called influencers on like TikTok. Anyway, here we go. So we're going to vote on this. Which one hits first? Hopefully this is an easy vote, okay? So think for yourself. You can discuss if you want. Vote on this. All right, so I guess technically there is a third option. Third option is do they hit at the same time? So how many of you think the paper will hit first? Thank you. All right, how many of you think the book will hit first? Nathan, you vote on this? Okay. And how many of you think they're going to hit at the same time? Super simple situation. So already we got an answer that Spainhour is a liar. Now those did not accelerate the same amount. Yes? Okay. But what was our two assumptions to get to kinematics? Acceleration's constant, which we actually somewhat have already proven to ourselves by that shape on the lab. So, okay, that's out. But what was the other assumption that I told you about? What are we going to ignore?
Friction.
Air friction. In truth, though, can you actually ignore air friction? It's there. Now, we can make it almost nothing. We can't actually work on that. So let's work on that real quick and see if we do somehow eliminate air as an issue, whether or not this actually does hold up. So let's start off easy here. I still think look a little bit more difficult than the last one. Here's what I'm going to do, people online. I'm going to put a piece of the book, all of it, okay, on top of a piece of paper. And the question changes after when I drop these, do they stay together or they separate? Discuss quickly in your group what you think is going to happen, what you predict. We'll vote and we'll move on. Discuss.
Sure.
It's like searching. It's gonna like stating that you get higher.
All right, here we go. We're going to vote on this. Take whatever information from the people around you and go one way or the other. I don't necessarily go with trust the smart person or whatever. A lot of people are usually wrong on these. But here we go. How many of you think they're going to stay together? And how many of you think they're going to separate? Offspring fans, keep it separated. Okay, here we go. Let's find out. Hands. All right, they stay together. Okay? So here's what some people then start to think, okay, well, the heavy book, we saw it earlier, it accelerated more than the paper. So in that particular vein, the thought process might be, I'm not saying it was, that the heavy book pushes the piece of paper to the ground. Yes? But here's the deal. If I'm right, and I'm going to straight up describe to you what's going to happen if I'm right, and I still don't think some of you will believe me, but it's fine. I'm cool with it. I've come to terms with it. If I am right, and I put the piece of paper on top of the book, I'm putting the piece of paper on top of the book. Okay, I put the piece of paper on top of the book. Okay, air will not get to the piece of paper anymore. And if air does not get to the piece of paper, and I am right, it should accelerate at 9.8 meters per second squared. When I'll let you figure out what's going to happen there. But you discuss, are they now going to stay together or separate? Based on, do you think Spain's a liar? I say it's fine. Okay, if you believe that, you believe that. So go ahead, discuss in your group. Will they stay together or separate?
Right.
You gotta keep them separated.
Yeah. I listen to literally everything. I kid you not. You will hear some days I will be listening to Offspring, other days I'll be listening to the Ribbity Raps. Sometimes I had to describe that. I'm a short line too. It's just kind of like it naturally comes out that way. But yeah, I mean, Tupac, Biggie, all the way back to Rakim, things like that, and obviously over to just classical music in general, so all over this. Anyway, moving on. Yeah, just all the stuff. Okay, please, yes. I said Paramore radio station on the other day. Who's I listening to that's very similar to Paramore that somebody described Paramore? Well, Evanescence, sure. I mean, those are they're not. But okay. All right, let's get into this. We've got other stuff. We'll talk about music taste later. Here we go. All right. Vote. It's got to be true here. I basically told you what I thought was going to happen. So let's see what you think. How many of you think they will stay together? This is the number of people that believe me. Okay, so this is the number of people that think Spain is not a liar. So how many of you think you got to keep it separated? With the rest of you. Where's the hands? Put up the hand. Okay, I'm not seeing votes. Also, I'd like to point out that the votes early on were up here. Okay, right now, okay, I want to see votes. Be proud of wrong answers. Here we go. How many of you think to stay together? Put up an answer one way or the other. Okay, I like the belief. Here we go. All right, and how the amount of years that I have done this, set this up exactly the same way, and no one, absolutely no one trusts me, is hilarious. All right, and so how many of you think separated? Okay, you're a little bit sad right now. You don't want to do it because, like, Spain was called out the fact that you're calling him a liar, but to be fair. Now, Jimmy Fair's you as well. Spain now is short, so perhaps it's just a height thing. But even better than that, according to what I just said, is that if air is a non-issue, then everything should accelerate at 9.8 meters per second squared. And if everything accelerates at 9.8 meters per second squared and you get air out of the way, of course they should land at the same time, which they do. Everything accelerates at 9.8 meters per second squared when you don't take air into consideration. Where is the closest natural vacuum to us? Space. Okay, let me change that differently because you are right. It's not what I was looking for, but it's because I asked the question, not because of your answer you gave. Where is the closest place that has a natural vacuum and still gravity? The moon. Yes. So this is why when we went to the moon, this is one of the tests that they actually did. They took a hammer, they took a feather, they dropped them next to each other, and what did they find? They hit the ground at the exact same time. And of course you could do the moon landing thing. I don't think any of you think that. Science works for you right now. Oftentimes you believe it, not because you actually believe it, because science is doing well and you're doing well in class, and so science must be accurate. Okay, as opposed to the people that usually don't believe in science because it's not working for it. It's fine. That's a whole other conversation. Point is, they've tested this. You can do this in vacuums here on Earth as well, which I'll actually show you videos of in just a second. If you have no air in the way, everything on Earth accelerates at 9.8 meters per second squared. This example was meant to prove that. Now, that being said, even though I proved it, it should still feel weird. If it doesn't feel weird to you, I question your skepticism. Good scientists are skeptical. They should look at stuff even when it's happening before them. There are things I will show you in this class. They will happen before your eyes. And if you don't think that maybe that's Photoshop, I question your logic. And this does, in fact, look weird. What I just said is if I drop a feather and I drop an elephant next to each other and there's no air, which one hits the ground first? Same time. And if that doesn't feel weird, we'll address this, why it actually is, in chapter 4. But the layers in physics just go deeper and deeper and deeper because we start here. We'll talk about it in chapter 4, and then if you really want, you can come over to physics 2, work all the way through the year of physics 2, and we'll discuss a little bit of general relativity at the end, which throws things entirely out of the mix. But let's discuss something further here. I need someone to be in a hypothetical example. It's entirely hypothetical. You guys have worded a problem yesterday. You talk a decent amount in here. But I don't Tyrez is kind of like quiet, but let's okay, I like it. Okay, we'll go Tyrez. All right. No comment on this. I was just choosing an example. We're going to drop Tyrez out of a plane without a parachute. All right. Hypothetically. All right. Okay, my drawings are terrible at Tyrez. This means nothing about your actual person whatsoever. Okay, here we go. So we drop him out of a plane. No parachute. All right. There's a reason. It's not just for fun. Okay, so not only. So imagine next to Tyrez is a piece of sheet metal. There's reasons. Okay, and Tyrez has in his hands a marker here, and he reaches out and he makes a mark on the metal. Okay, and we're going to go ahead and assume no air resistance here. So they got dropped together. What does that mean happens as they fall?
I'm gonna say the same
Why? Agreed. Why?
because there's no air.
Sure. So what are they doing?
They're
Gravity's
accelerating at the same time.
So they are going down, right? They are traveling down. Okay, but they're just going at the same velocity. Why are they going at the same velocity? Because they started at the same velocity and it's still changing. So they're both speeding up, yes, but they're speeding up together. This is kind of like if you're sitting in a car with somebody else, the car speeds up, you both speed up the exact same amount, you're going to sit next to each other, yes? So he makes this mark as they fall, he should see this mark stay roughly at the same spot, yes? Okay, now let's go one further. Use your imagination here. My drawing's not going to do the heavy lifting. Let's say there's a piece of sheet of metal below him. What should he see the piece of sheet metal below him do as he falls? Should stay at the exact same distance because it's going the same speed. Yes? You know, who cares because they're falling, one of them's falling to their death, the other's an inanimate object. But let's say we compose Tyrese entirely in a box. What does he see? Nothing. He's in a box. 100%. Okay, so let's put a light in there. We'll put a generator. We're doing a lot of work to kill Tyrese, but it's fine. Okay? Generator he can perfectly see right now. Don't miss this. This was the key of this. He's not going to die. It's only hypothetical. What does he see as he falls?
The sky or bottom.
No. There's no window. It's a box.
He's in the same shape.
So what does it look like he's doing? Floating. Is he actually floating? No. He's accelerating. He's accelerating at 9.8 meters per second squared. Of course, this is really obvious, but now I tell you this. On the International Space Station, is there gravity?
No. Wait, yes.
You never thought about that before, did you?
No.
On the ISS, the International Space Station, they're floating around. You've probably seen videos before. Do they float or not? Is there gravity? It's AI? Okay, that's good. Okay. We've talked about this before. If it's a simulation, it's a great simulation. Let's talk about the simulation. Okay, fair enough. But if you watch them, you see they're floating. So you would say no gravity. Except when you think about that, if there was no gravity, which direction would the ISS go when it was traveling?
Yeah.
Straight. I'll draw a picture. Here's the Earth. Here's the ISS. No gravity. And the ISS is going that way. Which way is it going to go? That way. So which way does it actually go? So is there gravity?
Yes.
Why the heck are they floating? Because they are going the exact same speed as the ISS. As a matter of fact, a good way to put this is the ISS is not in orbit. The ISS is always falling. And it's falling. It's actually not 9.8 up there. We'll talk about this later. It's closer to about 8. Okay? It's falling at a rate of 8 meters per second squared. But so is everyone inside. So what does it look like they're doing? Floating. Are they actually floating? No, that gets into a weird situation. So let's change the situation. Here we go. Let's try again. Let's put Tyrese in a box that won't kill him. A different metal box. Put a bunch of people in this different metal box. And we fling this metal box up into the air. Added bonus of that particular metal box is since they are encapsulated inside a metal box, are they going to get hit by air nearly as much? No. So what is their acceleration going to be pretty stupid close to? About 9.8. And right here, they're going to turn the engines off of that box. Okay, only briefly. They'll turn it back on, probably. Okay, while it's up there then, it's going to start falling at an acceleration of about 9.8 meters per second squared. And so is everyone else inside. And so what is it going to look like they're doing? Floating. When in fact, they're really just skydiving without a parachute. They just happen to have a giant metal box around them that has the capability of flying, so they don't have to worry about that parachute in that particular process. If you don't believe me, I've made a series of videos, a whole playlist that is already up here, and we'll start with the first one, and we'll finish the rest of this time, last 13 minutes, just showing you a series of videos related to everything I've said so far. This will be posted online, so if you're interested in looking deeper into this subject, you certainly can. Or if you don't care, watch with the direction of the hand there. German. All right. Woo! Coming at me pretty darn strong here on a Friday. Okay? I don't have the, listen, we already have way too many Nazis in America right now. Sorry, political commentary, but here we go. Here we go. So, a gravity playlist. Let me do my playlist, and I'll come back there and address your question individually. The video you are about to see, as it's going to tell you, is in fact 100% real. There is no Green. It's going to say that. Sorry, it's shot in 0 gravity. There's no actual green screens whatsoever. Come on, stop, do the thing. Thank you.
I've seen this movie.
Hooray! Good for you. Walk it.
Upside down and inside out, and you can feel it. Upside down and inside out, and you can feel it. Don't know where your eyes are, but they're not doing what you said. Don't know where your mind is, baby, but you're better off without it. Inside down and upside out, and you can feel it. Don't stop, can't stop until you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you're pretty sure you can't break. So when you met the new you, were you scared? Were you cold? Were you kind? Yeah, when you met the new you, did someone die inside?
Are they following the
Don't stop, can't you stop? It's like a freight train.
video? Is like 3 minutes
Stop,
long.
can't stop till you feel it going down. Don't know where your eyes are, but they're not doing what you said. Don't know where your mind is, baby, but you're better off without it. Looks like it's time to decide. Are you here? Are you now? Is this it? All of those selves that you tried, wasn't one of them good enough? 'Cause you're upside down and inside out, you can feel it.
Real quick, one of my favorite things to do with my imagination right there is think about, like, you obviously can't see out the windows right now. And they kind of, I don't know if that was done with the actual windows themselves or actually in post, but what would you see right now if you could?
The edge of space.
What's that?
The edge of space. That really.
They're not in outer space, man.
No, but like you see the planes where like they go like. To
What would it
the
look like the plane is doing if you watched outside the window?
No static.
It's falling. So one kind of thing to think about is, like, if you could, like, evaporate the plane in a second, what would it look like they are currently doing? They're falling. They are actually in the process of kind of skydiving. They just happen to have the plane around them while they're skydiving, and the plane, despite the fact that it is like 200, probably like 1,000 times what their mass is, still accelerates at 9.8 meters per second squared, just the same as they do. So they fall together, just like Tyrese and the plane, right? But they survived. Tyrese would not have in that situation. He would have died. Also, it would not have taken him 3 minutes to hit the ground.
Inside down and upside out, you can feel it, feel it. Don't stop, can't stop, it's like a freight train. Don't stop, can't stop till you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you're pretty sure you can't break. Upside down and inside out, and you can feel it. Don't stop, can't stop until you feel it going down. Upside down and inside out, and you can feel it. Don't stop, can't stop until you feel it going down.
All right. Why were they definitely not falling the entire time?
Because they would have crashed.
They had fallen for 3 minutes and 24 seconds. They would have hit the ground about 2 minutes and 30 seconds ago. Okay? So obviously that's not the case. Even inside of that, what other proof did you have that they definitely did not fall the entire time?
They went back down sometimes.
What's that?
They went back down sometimes.
There was about 8 separate sections in the video where gravity turns back on. Okay, that's actually where they come out of the pull in all actuality. By the way, I'm going to briefly describe this if this is interesting to you. I love this idea that OK Go is combining kind of music videos and the rock genre on top of like physics and knowing this. They did all of this. There's the behind the scenes video in this playlist if you are currently interested. It also talks about the timing of a measure and how it's like 27 seconds, but the way they fell was actually like a different distance, and so they spaced out. It's a really interesting thing. But yes, what they will tell you is that in that, what they actually did is they did fly 8 separate parabolas going up, and you can see them spotted by when gravity turns back on in them. There's a very specific time because it coordinates directly to how much time they fell, as well as how much time the particular measure at this particular pace is always going to take. Interesting. But let's say this is too produced for you. So you're like, yeah, okay, I still think that's a little bit green screen. Hopefully this less produced video will be an even. Oh, no. Listen, be faster. I clicked. I didn't click it.
Can we
No,
copy
I
the
don't want that one
wind
yet.
and,
I'm getting there. It's Apollo 13, 14, not 14. Less produced, even less produced, and hopefully, hold on, I'll get to that in a second. Oh, stop. Okay, even less produced than that. Have you ever gone over a hill too fast? Go over a hill too fast. What does it feel like in your stomach? What does it feel like your stomach is doing?
It's like a roller coaster.
It's kind of like your stomach is almost like floating inside your body, yes? That's because it is. 100%. You, in this particular instance, take the place of the plane or the box that Tyrus fell in. And your stomach takes the place of the person inside, and it falls just the same way. And just as you would float in that scenario, as you go over a hill too fast, you kind of briefly touch a little bit of free fall for a little bit of a second there. And so your does come up inside your body and does kind of float inside as you come to the ground, which you're certainly not used to because your stomach is usually that way because of gravity. All right, what you're looking at here, I'm going to skip around this video because we don't have 4 minutes to talk about this. This is, again, you can watch this. Brian Cox went to the world's biggest vacuum. Okay, he's British, so don't blame him for the way he says it.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out 30 tons of air in this chamber.
30 tons of air. I want you to stop and hear that because there's always something weird about air. How much air, if I took all the air in this room and combined it into one spot, how heavy do you think it would be? With all the air in this room. Big, small number, what you got? Make a guess. Make 2 guesses, I'll move on.
200 pounds.
What's 100 pounds? What do you got?
20 pounds.
It's about 1,000 pounds of air in here. Okay? Why don't you feel like it is 1,000 pounds? It's a whole density conversation, but we'll get to that a little later. Yes, 100%, because it's dispersed, six of them. Okay, anyway, they're going to pump out 30,000 pounds of air. It takes about 5 hours. They don't show that on the video, thank goodness.
Until they're
what they do is, well, actually, I'm getting into this. First thing, they're going to drop a bowling ball.
Galileo's
and a feather.
experiment was simple.
What's going to happen is what you
He took a
expect
heavy
to happen.
object and a light one, and dropped them at the same time to see which fell fastest.
It's going to happen. Expected that to happen. Moving on. So then, they pump out all the air, or he says air. All right. They make it very dramatic again.
Release.
Moving on. Just a heads up, I don't love that they do this because it makes you feel like it would fall slower. This is a slow-mo video. It would, in fact, fall at the exact right pace. But yeah, this is exactly how they would fall. Right next to each other if there's no air in the room. A feather and a bowling ball would hit the ground at the exact same time. Skipping ahead. That is the unnatural way to do it. The more natural way to do it is what we said here at the beginning of class, or towards the beginning.
Can we copy the boat shoulder wind and penetrometer drum in the EPD?
We'll say it's Apollo 14, okay? You'll wait just a second. It'll be more obvious in just a second when it pops into the video. There's a little lander behind him.
Yes, I will. Shortly. I want to watch this. Oh, a good picture there.
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two up here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct.
One of the best proofs, by the way, that the moon landing is not fake. Not that they fell together, but that if you time that and look at the distance, the acceleration that those go through is not 9.8. It's 1.67. That would be it'd be fine to fake them going next to each other on Earth. It'd be real darn hard to fake that the gravity is different on a soundstage in Los Angeles. Anyway, last video I'll show you real quick and then I'll move on, mostly because it's just funny and I find it absolutely hilarious. Because the gravity is so much less on the moon, that means you would weigh less on the moon, which you've heard, but you are used to weightlifting your weight, as are these astronauts as well. Astronauts are some of the best athletes, one of the best individuals. They're the best humans that we have to offer. And yet, if you weighed 180 pounds and automatically started to weigh 30 pounds right now, yeah, you'd probably fall over a lot too. So this is astronauts falling over to SpongeBob music. Oh, you dropped it. No, oh, buddy, I'm sorry. Come on, you got this. Okay, you got it. There's a rock there. You didn't see it. I'm sorry. Okay, oh, no, he's falling so slow, he doesn't even realize you're falling. You're falling. He's like, Just like do a push-up. Do a push-up to push yourself back up. You got this. You too. Hold on, I'm gonna watch this. I want to see if he makes it. Oh, so close. One more time. Come on, you got this. Almost. Oh, poor guy. One more time. He's got it. So, what's up?
If we push him so too hard, we need to
Do I still have it? Yes, I haven't got a chance to finish reading it. That's the one. Oh, okay, sure. Let's just do this. I got it. They do end up, they will still attract by phase magnetism. Obviously, gravity moves so many magnetism. When you break them, it's north and south. So north and south will still be together. Magnetically, very good. Thank you so much.
Where's that?